Welcome to my class again. My name is Omeri. Last time we reached on the relationship between frequency and periodic time. We say that the inverse of frequency 1 over f is equivalent to periodic time t. Therefore, the product of t and f is equivalent to 1. I gave you a number of questions to do. Now, have you done the questions? Let me know through the live chat or through the stream as we continue today on this topic. Introduction to waves. So the properties of waves that today we're going to be looking at is the wave equation. There's a relationship between speed, frequency, and wavelength. We are going to learn that this is an equation that shows the relationship between velocity and frequency. And therefore, speed v or velocity v is equivalent to f times lambda, which is wavelength, where v is velocity. We can represent this in the word equation by saying velocity is equivalent to frequency times wavelength. For example, a water wave of frequency 4 Hz has a wavelength of 3 meters. What does this mean? We know that waves are measured in Hz. Hz represent the number of circles the wave makes, and therefore in this case, 4 means that the wave is covering 4 circles in 1 second. The wave is covering 4 circles in 1 second. The wave is covering 4 circles in 1 second. The wave is covering 4 circles in 1 second. Now, what is the relationship between speed, frequency, and wavelength? We say that velocity is equal to frequency times wavelength. That is how to tackle that equation. Now, calculate the speed of the wave. We have been told that the frequency is 4 and the wavelength is 3. Therefore, we can say that the speed of the wave is equivalent to 4 times 3, which is equivalent to 12 Hz. Now, let's move to the next part of this topic. If you are supposed to calculate the periodic time, then to calculate the periodic time, you need to say that t is equivalent to inverse of f, which is 1 over 4, because our frequency was 1 over 4. By doing so, you'll be able to calculate periodic time t. But more specifically today, we shall be looking at the repo tank. So what is a repo tank? A repo tank is a device that is used to study the behavior of waves. So we can be able to say that the behavior of waves is studied using a repo tank. So we can be able to say we study the behavior of waves. We study the behavior of waves using a repo tank. Now, let's look at the features of a repo tank. At a close look at the repo tank, one of the features is the repo tank has a vibrator. The vibrator is this round thing that you're seeing. There's a tank and there's a lamp on it, and below below it there is a screen. So you can be able to see that this is the screen. This part is the screen, and this is where the water is. This is a vibrator like a moped, like a motor. Is the vibrator, and that is the vibrator. Now, in real sense, this is the demonstration of how a repo tank looks like. And there's elastic suspension, electric motor of center mass, then wooden board with two cape hooks. On turning on the motor, the wooden bar vibrates, creating a series of ripples, what we call wavefronts on the surface of water. We shall see that in our practical shortly. Light placed above the tank creates patterns of the wave on the floor. By observing the patterns, we can see how the water waves behave. Now, I want to see that. I want us to see that in a more practical way, how a ripple tank works. Explain how a ripple tank works. Let us see how a ripple tank works. Now, there we go.
Right, to start off, we're going to need some water, and we're going to fill that into about 5 mils depth. That should be fine. And then what I'm going to do is I'm going to add just a few drops of household detergent, and what that does is it reduces the tension on the water surface.
So we see this guy here just showing us what is being done here. The ripple tank. He must have the water, he must have the vibrator, and he must be able to have the other features.
Which means that you can just make better waves.
That's nice.
And I'm not going to try and make bubbles with that. I'm just going to move it around so it starts to mix with the water, trying not to make bubbles, because once we have the light on, any bubbles will show up underneath.
Sure.
And then to start off with, I'm just going to plug my light in. I can see the ripple tank isn't completely flat, so I need to adjust it so it is. I'm going to pull that leg just a little bit further in. This one. That one down a little bit.
We see this white.
Now I'm going to use a power supply. And this halogen bulb takes 12 volts.
There we go. We are making it. So when this power here, he was been joining this power.
I'm going to move
those
that
patients
so it's in the center
to join this power
over the tank.
Friday.
Now I can already start illustrating waves just by showing, for example,
so if this is very powerful, so you should again see the process.
Wave drop.
Now what you see,
And
the waves being formed here is great, and that's very important for us because we're in the station to be
see the waves on the table below the ripple tank.
Screen, yes.
So here I can make a little wave pattern, and I can see the little waves moving away from the drop.
Now, if you can see that, you are smart.
Linear wave, flat wave. I can use this bar over here. I'm going to put this into the water, and then without moving the whole tank, just move it back and forward like that, and then you can actually see the wave pattern underneath the tank on the surface. Do that regularly to create the waves. Right. Now, using the dropper and the bar, I can create circular or straight waves, and then use the barriers to show reflection or refraction and do my demonstrations. But then we also have included then that motor with the ripple bar, so I'm going to connect that up over here.
That's what we're in, the motor, you know?
Connect it to the side, there we go. Hang that. And I just want to, if I'm, for example, showing a single point, I'm going to have one of those pointing down then. And then I'm going to lower it until that ball is just touching the surface of the water. There we go. Then I can plug that into my speed controller, and that should turn on. And what I've done is I've got it on the minimum setting.
This is really the power station, is really the greatest capability that we can be able to look.
Here I have that wave pattern in the water. Now I can use my barriers to illustrate, for example, what happens if I have that circular wave pattern and it hits a barrier at 45 degrees. And then they'll be able to see the wave reflecting off. Now if I want to show a straight wave, then what I can do is...
In our video, we have been able to show you how a ripple tank actually works, and in the notes assigned on your portal, now you can be able to note down important points, the properties of wave. Now, let's move down. Reflection is a property of wave. It's the bouncing back of light. Waves. A wave coming at this point can be reflected back, though some of it can be refracted. So bouncing back is the property of wave. So at the point of incidence, we have the incident ray, the normal and reflected ray. It is important to note that in the reflection, theta I and theta I represents the angle of incidence and theta R represents the angle of reflection. Theta I is equal to theta I R. They are equal. For example, if I is 30, R is also 30. It's important to know that reflection is a property of wave. Refraction is a property of wave. A wave can change direction. This relative change in direction of a wave as it passes from one medium to another is called refraction. Sometimes you can say this is the bending of wave or light. Light is an electromagnetic wave. It's important to note that. So sometimes we can be able to say that the change in speed of a wave is the reflection of a wave. So far we have seen these properties of a wave: reflection and refraction. Doppler effect. We're going to watch a video on the Doppler effect. But first, what is Doppler effect? If you're in a car, for example, and the car is vibrating and it's not moving, then you're going to experience a uniform tonation or frequency of the sound, the loudness or the lawlessness of sound. Now, if you're standing and the car leaves you there and moves away, the sound of that engine fades as it moves away. Or if a car is approaching you, then its vibration increases as it approaches you. This relative change in frequency and wavelength, as due to the position of the observer, is called the Doppler effect. The Doppler effect can be demonstrated in a way like this. When you're in a stationary source, you, as the observer, you experience uniformity. Now moving a stationary observers. If observer X remains and observer Y, the car is approaching him, then observer Y is going to hear a louder vibration of the engine than X. Now, this relative change in frequency due to the position of the observer is called Doppler effect. Good. Now, you will check your work on 3.1, then you'll be able to do these assignments. Next time, we shall be looking at Unit 3.2. Now let's look at a video on the Doppler effect. So let's see what this white is saying.
The Doppler effect. In Sheldon's words,
it's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
The Doppler effect is perhaps best explained visually. So here's a thing that is emitting waves. It could be a fire truck emitting sound, it could be a star emitting light, it could be a duck creating ripples on a pond. Those are all waves, and they all look something like this.
And we'll be able to see
we see the Doppler effect happening when the thing that is emitting waves moves. In the direction it's moving, the wavefronts bunch up, and behind it they spread out. If our object is moving towards a stationary observer, these bunched up waves are observed at a high frequency, and if the object is moving away from a stationary observer, the waves are observed at a lower frequency.
So we can be able to see this. that it's important to know that the Doppler effect is a apparent change in the frequency of a wave caused by the relative motion between the source and the observer. Now let's look at that. It's important that now we know this. Other situations is part. Now let's go see what's going to happen between here. The Plato's portion the guy passes by him. The word page to see what's important here. So it's important the real pause vision. Now let's look at this. This guy's moving much more slower than the fast car, and be able to see what the observer is getting from the source. It's relativity. So that relative change in frequency due to the position of the observer, we call this the Doppler effect.
You see the light at a higher frequency than it actually is. Frequency in sound is pitch, so what does it mean for light? Well, if we look at our handy pocket electromagnetic spectrum chart, we'll see that a small change in frequency for visible light will change its color. Higher frequency light waves means bluer light, and lower frequency light waves means redder light. This is called redshift, and it may possibly be among the weirdest and coolest things of all time. Stars, or anything that you can see, change color depending on their relative motion to you. Of course, you can't see this minute difference with your eyes, but astronomers with the right equipment can use this effect to tell whether stars are moving away from or towards Earth. As it turns out, almost everything we can see in the universe is moving away from us very quickly, which is both an important piece of evidence for the Big Bang and an indication that the Earth might get very lonely in the distant future. Thanks for watching this video. Let me know if you got something.
So our lesson ends there today. Join me in the live chat and post all your questions. I'll be on the stream to answer all your questions. Also, be joining me on live chat on the live stream. If you miss out this video, find it on our channel, the e-learning channel. My name is Omeri Tobias. I'm online to hear you. What do you say on our stream classroom? Thank you.